Let's go ahead and get started. So I believe this is the last parallel session time slot. So this parallel session is on commissioning, and these are the reminders that we've seen the last couple of days. Let's all continue to be kind to each other. Do this. Could someone help with remote participation? I meant to ask before, but is someone looking? Okay, thank you, Yusra. just to make sure. Please, yeah. So please post the questions in Slack, and we'll be monitoring those. Okay, so here's the agenda for the next 90 minutes. So when putting together this agenda, we wanted this to be an open community-facing session. And we also wanted to make sure that we included enough detailed information that it would be useful for the in-kind contributors that are working on commissioning. And so you'll see overview information and then also some more detailed technical information about how to get involved. So the agenda has two parts. One is on the LSSTCam commissioning at the summit, which is one of the major activities. And then in the second half, we'll transition to talking more specifically about the upcoming ComCam on Sky commissioning period. And we'll hear updates from different groups that are thinking about that, and then how we're all going to work together to analyze that data and finally close out the project by demonstrating that the system works the way that we hope and expect it to. At the end, I'll have some time for discussion about information sharing during commissioning. So the first topic is LSSTCam commissioning at the summit, and I'm going to hand it over to Thibault to give the overview here.
Sorry. Okay, so yes, I'm Thibault. I'm working on the camera commissioning at IN2P3 in France, and I've prepared this slide with the help of Yousuke, who is at the summit right now. So just to get started, this is the official schedule or reference. So what concerns what concerns the LSSTCam is the yellow part at the bottom, and basically the reception was planned to happen mid-May, and this is what happened. And then there was a period dedicated to unpacking and preparation of basically 2 months until the start of the what is called the camera re-verification phase, which was planned to start mid-July. And I will comment in the next slide where we are. For basically 2 months period until mid-September, and then from the end of the verification period, again 2 months until the installation of LSSTCam on the TMA. I will show where we are. So the camera arrived mid-May, so there was basically no contingency with because of the flight preparation. And you have all seen the picture, so there were a lot of containers and a lot of material to unpack. And so there were, in the first week, a lot of activity really focusing on this. And without going into too much detail, so there was well, basically everything to set up at the summit, so from computers to network, etc. And everything related to the infrastructure work at large to have the camera ready for data taking first at L3. And there was also a lot of work in June and July on the filter exchange system. And basically the status for the filter exchange system is that everything has been requalified, except so for the filter exchange system, there are 3 parts: the carousel, the filter loader, and the filter I lost the word, the auto changer filter. And there is just the auto changer spare one, which has not yet been requalified, and it will come soon. And the current work is is really focusing on preparing the vacuum and the refrigeration systems to be able to have the camera cooled and ready to take data very soon. So a lighter version of the summary activity with just picture. So you have at the bottom left the camera protected, so in the clean room at the summit. You have then a filter loader in its storage box. Then you have work of test of the filter auto changer. Then there was also some cleaning of the lenses. Here you have a picture of L3. And very recently, just 2 days ago, there was some air hose installed. So really getting very close to have the refrigeration system being ready for use. So this is really coming in the next week. So basically, so there are two main parts for the refrigeration system. One part for the readout electronic, and one part for the CCD. So the cold chiller part is basically almost ready, and there is some remaining work to get the cryo refrigeration system ready. And then the roadmap is to establish vacuum and start the cold system and start the cryo system. And so the hope is that if things go smoothly, to have first test with reading what first exposure, first data taking test in basically 2 weeks, probably not next week, but hopefully the week after or the next one. One thing to mention, so there has been so far so there was a plan to have in July test with a glass filter at the summit, but this was not done, and so the electro-optical testing will be mainly conducted without the glass filter. So electro-optical testing just is the same as what is called the camera re-verification. The data that will be taken very soon at L3. So a bit more details about this re-verification campaign. So we will be tested the camera in the clean room at level 3. And so basically we take calibration data and data with a light source. So the light source will be the CCOB wide beam projector. And there will be more or less 4 phases for this data acquisition. So the first phase is really the bulk of the re-verification campaign. Is in simple word is to make sure that the camera performance is the same as before the shipping, or very, very, very close. So that will be really the key milestone. And then we would like to add to have a functional test with more with the shutter, the filter exchange system, and possibly using long tests with a realistic cadence, as it was done at SAC in the previous electro-optical testing campaign. And depending on the time that the first parts will take, we would like to do characterization and optimization runs because of several things we would like to study, if possible, before the camera is moved on the TMA. So if you want to see more details, there is a plan at this confluence page, and basically this goes from basic validation of the camera, which is, as I said, the key part, to optimization and characterization. So clearly there are things which are which have a lower priority, but one caveat is that there are things that we could not studies that we could not perform at SLAC because of the refrigeration issue, and so the previous EO testing was basically shortened. And one point is that once the camera is on the telescope, clearly the threshold to change anything related to camera configuration will be much higher. And so there are things that we hope we could fine tune before this step. Very briefly, just to give you how electro-optical test will look like. This is just 2 slides about the electro-optical campaigns that we performed at SLAC so last year. So in 2023, there were two campaigns, and basically from the picture, so you can see the test bench that was at SLAC. So it will be in some way a bit similar at L3 with a more constrained, much more constrained environment. And for instance, we can only have the camera in the horizontal position, not in the vertical position at the summit. And basically, so we took a lot of data, store them and process them at USDF, and analyze it. So the overall roadmap is the same, but with say, much tighter time scale and a much more constrained environment. And so far, not tested. So this was for the hardware. So for the software, we want to reuse what we used for the previous EO testing campaign. So the main tool is EO pipe package, which is based on the stack, and which basically produce a set of reference plots for each run, and the set of plots and metrics produced depends on the type of run. So for instance, just for illustration, you have a full mosaic of the readout noise, then a flat for flat exposure for raft, and then a PTC curve, so photon transfer curve for one amplifier. And so we will do repeat that for run 6 for the re-verification campaign as soon as we turn on the camera. Just two things that were nice and done during the previous campaign. So you have on the left for two CCD, one ITL and one E2V. So we have these two types, and this is the quantum efficiency curves using the CCO binary beam and scanning versus the wavelengths. And you can see for two different incident angles, and you can see the curves, the different behavior between the small different response between E2V and ITL. And on the right, this is one thing which was also performed and where we learned a lot. So these are so-called optim run, where we take very long stability runs, which consisted of basically 1,800 dark exposure, and we could really push the system to see how stable it is, and in terms of data transfer, etc. That was very useful. So final part, just one word about some update regarding organization. So since the start of the year, basically, the science unit has really ramped up. So this is the instrument signature removal detector characterization, which is coordinated by Chris and Yousuke. And basically, we have defined a set of topics. So basically, all the main sensor anomalies that have been identified in previous data campaigns. And there is a Confluence page where there are some details and people working on these topics. And this has really improved the coordination between say the various people involved, so from DM, from the calibration side, and from the camera. And one thing which will be very useful is that there is an operation rehearsal number 5, which is planned for the end of the year, and which will be based on a playback of LSSTCam data, so full focal plane data, and that will be very useful to have the production, validation, and calibration for the full focal plane, and have all the people involved working together. And just finishing with one word about operation rehearsal number 4. So the next one will be based on the full focal plane. So the previous one was based on the ComCam SIM calibration, and that was also very useful. So for the calibration, things were pretty smooth. So basically, they were built from the simulated exposure using CP pipe task, and then the validation was done using the CP verify calibration task. And without going into too much detail, you can see the table at the bottom, where you have the 3 days of the rehearsal, ComCam SIM day 1, day 2, day 3, and basically everything was done. The only missing piece is the propagation or storing of the calibration results to the Sasquatch database, which will allow to monitor the calibration behavior versus time. And just to illustrate the calibration results, so there is a report which is still in development, but which has already made nice progress. And for instance, here you have for the full ComCam raft, so ComCam SIM raft, the readout noise level per amplifier for the calibration. The calibration product, and on the right, one histogram version. So you have the 144 amplifier. So there is still some work ongoing to fine-tune these and to scale it to the full focal plane. All I have. Oh, okay. Thank you.
Any questions on LSSTCam status of the summit? Okay. Thank you, Thibault. Okay, so next up, we'll talk about the ComCam on-sky commissioning. And so let me pull up a summary diagram. So this is our overview timeline that we use to regularly communicate the status of commissioning. And so we just heard about one branch, which is the LSSTCam arrival at the summit, the checkout that it arrived safely, the reintegration of all the infrastructure, the re-verification, and then eventually the installation on the telescope. So that's one branch. While that is happening in parallel, we're getting a jump start on the integration of the telescope and the beginning of on-sky testing using the commissioning camera, ComCam. And so on this upper branch here, you can see the work that's been happening to prepare the telescope. We were recently, the last news that we heard was that the M2 glass was installed on the cell on level 3, which is our staging area at the summit. And then just yesterday, that M2 cell and glass on it was installed on the telescope. So as of yesterday, this is the first time that we have had glass on the telescope. Yeah. So that's a huge milestone for the summit integration team. I think if you have details about all that work, I see Brian Stalder in the audience, and there's probably other people who can go into detail about what's been happening at the summit. So that is a major milestone, a huge amount of work by the team. The next step is that because of the way that M2 and ComCam are positioned on the telescope, you have to have the telescope pointing at horizon. M2 drops in from above, and then ComCam will go through the open part of the annulus of M2, and then at that point we'll have the whole top end assembly with ComCam and M2 on the telescope. So the other part that's been happening is that the M1, M3, the combined primary tertiary mirror, that has now been coated. So there's the silver coating on that. The performance is excellent. It's at specification or better. And all of the infrastructure that is beneath the silver coating, all of the infrastructure of the cell, that is now being reintegrated on level 3 below the coating chamber. So the current activity is putting in all the actuators that will control the surface figure of the mirror. And I think probably Josh may talk a little bit more about how that's going to be used when we get to the AOS active optics system commissioning. So the next step will be point telescope back at zenith, and then like a train, the M1, M3 mirror will come in horizontally. And then at that point, we have all of the optics installed, and then we can take the first on-sky images with ComCam. That's currently slated for kind of early September timeframe. So the idea is that while this re-verification and checkout of LSSTCam is happening on the summit, we're observing with ComCam on sky for roughly 2 months. So sort of September, October timeframe. ComCam will come off the TMA to make room for putting LSSTCam on. And then at that point, we just have a single track. At that point, we're in this sort of upper cyan blue part of the diagram. And then, so we go through an initial period, LSSTCam's installed, it's cooling down. We take our first images, engineering activities. We move on to the science validation surveys, and then onto operations. So that's the big overview of the timeline. This other view is included in the slides, if it helps you to see it in this way. Okay, any questions on the overall timeline? As you can tell, we're very excited about this. Yeah. All right, I'm gonna hand it over to Josh to talk about the active optics system.
Thanks, Keith. Yeah, so the first time I made this slide, it was about 200 days. It's been converging at about 0.8 seconds per second since then. But yeah, we're at about 6 weeks now. Yeah. All right, so I wanted to talk about the commissioning plans for active optics. So start with a brief overview of active optics. So, you know, the telescope fundamentally is tens of grams of silver that we have to keep in very precise position to tens of nanometers accuracy while we're tracking and slewing around the sky, right? That's the telescope. Gravity and thermal effects make this difficult to maintain, but we do have a number of knobs we can manipulate to keep things at that 10 nanometer precision. There are hexapods that can align M2 and the camera with respect to M1, M3. There are actuators under the mirrors that can subtly change the figure of the mirrors. And then on the LSSTCam, we have these corner wavefront sensors where there are CCDs deliberately in and out of focus. And it turns out that those in and out of focus images are more sensitive to optical perturbations, misalignments, misfigurements than the in-focus data. So we use those on LSSTCam to infer the correction we need to apply to get back to this 10 nanometer precision. For ComCam, of course, there are no split CCDs, there are no intra and extra focal CCDs, so we'll have to piston the full camera in and out of focus to get the data we need to infer the state of the telescope. Right, so what are we actually planning to do with ComCam for AOS commissioning? The goal is to use ComCam to get the rest of the system, you know, everything except ComCam, into the state where we can start observing with LSSTCam. So we're gonna get an initial alignment of the telescope, collect some initial data products I'll describe in a minute. And I'm sure we're gonna gain a lot of how-to knowledge as we go, you know, as we learn how to update data products in real time on the summit. Do that first on ComCam and be good at it by the time we're on LSSTCam. So the tests, we have planned, to collect these data and verify things. I've broken them into kind of 3 categories. There are verification tests where we're kind of looking at how well does the software go from these out of focus donut images to the state of the system. There are data products we just need to collect. So this is lookup tables, which will be the primary way we set the degrees of freedom. Sensitivity matrix, which is how do the optics, the actual light wavefront change when we manipulate a degree of freedom in a reference wavefront. So what is the kind of nominal state of the wavefront of the optical path through the system? And then the third category is optimization. So when we're actually using the wavefront sensors to make corrections from one image to the next, what are the optimal gains and penalties to apply in that procedure, that feedback procedure. And then we want to do all of this under different conditions in the observatory. So for, this has to work in different seeing with different filters, different pointings, including the rotator, different wind conditions, different temperatures. It has to work across all of that. And we have to keep in mind that some of these measurements and tests will transfer better from ComCam to LSSTCam than others. So we don't want to waste a lot of time optimizing things that won't help on LSSTCam. Right, so first photon, 6 weeks. So we expect some restricted, reduced functionality of the telescope at first. So for glass safety, we may only be at 1% slew speeds at the beginning. We'll probably stick near zenith for that because we can't slew very fast, and also because our initial estimates of corrections from lab measurements were all done at zenith. So we think we know the telescope better at zenith than we do at horizon. We have a laser tracker at the summit that can get a coarse initial alignment of the camera and the 2 mirrors. So we expect that to be running and hopefully performing well. Probably the first thing we'll do is coordinate systems. There are a lot of minus signs to keep track of. So the easiest way to get those right is empirically, not by like staring at your simulation code for hours, right? So things we can do are look at the edge of the dome slit, right? We know what side, should be occulted on the mirror by staring at the edge of the dome slit, and we'll see what actually shows up on the image. Is it what we expect or not? Similarly, we can close petals that cover the mirror, individual petals on the mirror cover, and we can make sure we understand, are we rotating clockwise or counterclockwise with the camera rotator. We expect to be doing pointing tests during this time also. So we're building the pointing model, or refining the pointing model that's already been developed using the star trackers. And probably we'll be doing focus sweeps early on. So that's what's plotted over on the right. This is an analysis of a focus sweep that was part of operations rehearsal 4. You can see, there's a nice parabola when we change the camera Z hexapod position on that plot in simulation. And then I'm sure we'll start some of these verification tests. So these includes things like, if your donuts are blended, what effect does that have on your analysis? Can you account for that or cut those out and still get the same results? What happens if your donuts are vignetted? They're close to the edge of the field and some of the light gets cut out, things like that. So data products we need to collect. So I mentioned lookup tables. So we have initial lookup tables. These are basically what are the degrees of freedom as a function of primarily elevation angle of the telescope. We have values that are a combination of finite element analysis and laboratory measurements from the mirror acceptance testing. We will want to refine those and also build tables that depend on other variables like the azimuth. Hopefully that, we don't expect a strong azimuth signal, but we're going to look for one. The camera rotator will also look at temperature. We can't directly control that, but we'll regress with the data that we do collect. to see if we can build a lookup table that includes a temperature term. And we'll check for hysteresis. We can sweep up and down in elevation and make sure the results stay the same going up and going down. We will measure the sensitivity matrix. So that's what this is showing on the top right plot. This is actually done on Oxtel, where we intentionally displaced the secondary mirror hexapod and watched, you can watch how the donuts evolve as you're moving the hexapod back and forth. And then the bottom plot is an analysis, a quantitative analysis of those images. So we're going to do that for all 50 degrees of freedom. We'll probably repeat some of those degrees of freedom in different filters, different conditions, and we will refine and verify what we already have predicted from the finite element models. And finally, we'll collect a reference wavefront. This can be useful for understanding the covariance of different terms in our analysis of the donuts. Basically what this is we're just going to stare at the sky and kind of do nothing but collect lots of donuts, and we'll see how the atmosphere impacts, changes from one exposure to the next. And one other thing we can get out of this is actually we should be able to get a focal plane height map for any discontinuities in the 9 ComCam CCDs in the focal plane. And then finally, we'll do some closed loop tests. So what this means is actually applying feedback by measuring the state of the system, and then applying corrections and trying to get a better image in the next iteration. So this is going to be intrafocal, extrafocal, and in-focus triplets. That's going to probably be our primary observing strategy for AOS. And let's see, we don't have the corner wavefront sensor, so we're going to have to piston the camera up and down to get the donuts. That's what this triplet system is. We'll have some tests where we apply a perturbation and make sure that the feedback brings us back into alignment. We'll use this to optimize gain and penalty coefficients in the controller algorithm. And we'll investigate degeneracies. Degeneracies is an interesting problem for our system. We have 50 degrees of freedom, but only about 30, 35 completely independent degrees. So we have to figure out how to deal with the degeneracies in the system. We'll start by just restricting that set of degrees of freedom to a smaller number and kind of adding them more gradually. Right, and then the strategy, like I said, we're gonna be doing lots of triplets. Where we are in the sky, we care more about azimuth and elevation than RA and DEC. So we'll probably do things like stick at one ASL for an hour and do some test and just let the RA and DEC cross the sky, sweep by. And like I said, we have to cover a wide range of conditions. So okay, that's it. Yeah, Nevin. Oh, sorry.
So what I was just saying, you are going intrafocal, extrafocal, then you're applying it in focus, and that will take some time. And is the assumption that you hope that the atmosphere changes little, or like that obviously is not optimal?
Yeah, it's not the same as the LSSTCam where everything's collected simultaneously. Yeah, so we are relying on things like the atmospheric effects to not be changing too much during that time. It also, and like you mentioned, it takes time. So, the time between the interfocal exposure and the extrafocal exposure is probably more like 45 seconds, even for a 30-second shutter opening.
And all of the things that you described, they were on the sky, right? Or most of them?
Sorry?
On the sky, on the stars, these plans that you were describing.
This bias?
On the sky, I'm sorry. Yeah. Okay.
Yeah.
Yes, I have a related question. My understanding is that dome seeing may be a problem, especially early on. And in the context of Nevin's question just now, is that going to cause additional challenges in all the work that you just described?
Yeah, we might hear more about dome seeing in the next section, but I can say there are a couple levers on the AOS side that we can still manipulate to attack dome seeing, things like the exposure time. We can average over different amounts of integration times. We can change the amount of defocus we use also, which is actually something we don't have that lever on the main camera, but we do on ComCam with the pistoning.
Maybe that's what you're showing here, but do you have simulated data, simulated ComCam data with those donuts, with like blended donuts and things
Yep.
like that? Okay.
Yes.
And has the calibration been exercised on it? Because I think it would be nice to test, we can do like ISR and stuff like that.
The ISR stuff. Yeah, so that was all part of operations rehearsal 4. We had ComCam donut simulations, and it went through the normal rapid analysis pipeline, including ISR, for example. It seemed in simulation, it was fine. We'll see what happens on Sky. Thanks.
Okay, so thanks to Josh. So as we heard, there's several other factors that affect the overall delivered image quality besides the optics themselves. And so we're going to hear from Elana Urbach, who's going to be speaking remotely about how that testing will go with ComCam.
Yeah, thanks, Keith. Can you all hear me?
We hear you well.
Okay, great, thanks. Okay, so the goal of the ComCam image quality team kind of during ComCam is to find our largest sources of image degradation and begin figuring out how to mitigate them. And what was just mentioned in one of the questions is we expect that dome seeing, frankly, also perhaps mirror seeing, to kind of dominate the other sources, at least as first. And so our plan is to use a combination of telemetry and specialized imaging techniques in conjunction with AOS to kind of start to figure out what these sources are and figure out what we can do to mitigate them. Next slide, please. So for telemetry, I'm just going to go through kind of the big tools that we'll have available to measure atmospheric seeing, which we're not going to correct for, but which will provide us a baseline for our optimal image quality. We have the DIM, which will be on continuously during ComCam. For dome seeing, we'll have a few different options. We'll have multiple 3D anemometers, which can give us a standard deviation of sonic temperature, which will be a good proxy for dome seeing. We'll also have a fast star tracker on the TMA, which will act as an in-dome dim. And we'll have some ability to control temperature. We'll have an HVAC system. We will not have control of the louvers and other things, but we should begin to be able to start to understand our dome seeing problem. For understanding mount motion, we'll have mount encoders and accelerometers on the TMA and on the mirrors. For mirror seeing, we'll have mirror temperature sensors and a coarse temperature control. We'll expect finer temperature control when we have during LSSTCam. We'll also have access to a weather station outdoors, and we'll be able to, of course, walk around during the night with thermal cameras, see if there are other heat sources that we're missing. All of this telemetry will be stored in the visit database, so we can easily correlate it with the visits that are and the measurements that are taken during AOS. And perhaps we'll have additional telemetry, but I do think this will be enough to kind of get us started. Next slide. And then for specialized imaging, we have 3 different techniques that we'll be using during ComCam. We have pinhole imaging, which is more for finding stray and scattered light. We'll also have streaked and stuttered imaging, which is basically taking short exposures with ComCam, doing a partial shift in rows while not reading out the CCD, and then doing another short exposure, which will allow us to kind of probe the 0.5 to 100 hertz kind of regime, and should allow us to some extent to disentangle dome seeing, ground layer seeing, upper atmospheric seeing, and mount motion. We can do potentially to some extent the same with guider mode imaging, which is just looking at a small region of interest on our CCDs, but at a kind of 9 hertz rate. And so these are kind of the 3 additional techniques that we'll use in conjunction with AOS. The amount that we'll use them versus concentrating on other imaging campaigns will depend on how well our telemetry works, and I guess to some extent also how well AOS is able to explain the sources of image degradation. But these will all be in our toolkit as we go on Sky for ComCam. Thanks. Are there questions?
Any questions for Elana online or in the room? Okay. Thank you very much, Elana.
Thank you.
There's big applause in the room if you can't hear it. Okay. So interwoven with those engineering activities that we just heard about, we have the goal to try to put in as many science commissioning observations as we can. So this is a reprise of some slides that some of you may have seen at the early science session, but I'll go through them quickly just to provide the full context. So when we say the science commissioning observations, this includes the science pipelines, the tuning up that we'll hear about in just a moment, as well as using the science pipelines to learn overall about the data quality that's being delivered by the system. So as the active optics system and our image quality testing is maturing, we expect the ability to deliver good quality seeing over a range of elevation angles to be improving. And so we have a stage series of tests that we want to do on the science side that begin with tests that are maybe have looser requirements in terms of the delivered image quality. And then we'll be progressing to observations that are kind of like small surveys in limited regions of the sky. So initially we'll try to, our plan is to take every in-focus image and push it through the science pipeline. So that'll begin even during the active optics system commissioning tests, move on to exposure time scans and bright star scans, and then the series of having a pointing center and then doing dithered observations to various depths and in areas. We may not be able to get to all of these during the limited time that we have on Sky with ComCam. As I mentioned earlier in the week, in terms of the band selection, we expect to start with 2 of the GR and I filters plus a pinhole filter that we can use to study stray and scattered light. Once we have done some initial testing with the AOS and image quality, we hope to have the full complement of GR and I. And then as the image quality is improving, eventually swap in the UZ and Y filters. For the field selection, we expect that initially the observations will be constrained to be near zenith. And as we're able to verify the performance of the lookup tables over a wider range of elevation, then we'll start taking observations of a range of air mass. I'll just point out that during the AOS testing, it may be that many of the individual visits are scattered across the sky in RA and DEC because we're intentionally sampling telescope elevation and azimuth. And then once we get to the small field science programs, our goal is to really try to explore a wide range of parameter space in the sense of stellar density, some fields near the ecliptic plane, some fields overlapping external data sets. In terms of the duty cycle, again, we're planning to take every single frame, basically every visit, and put it through single frame processing, starting from the first in focus image. And then over time, as we're going through the ComCam on Sky period, we'll be transitioning from mostly engineering activities to, we hope, a larger fraction of the time for the science programs. This is an example of what one of those small field science programs might look like. We call this a dense dithered star field in the sense of densely dithered. So basically many repeated pointings around a field center. And this visualization here is using the feature-based scheduler that Lynn Jones was talking about this morning. And so what we can have is a series of different fields that we've put into the scheduler configuration. And then throughout the night, the scheduler configuration will be moving between those fields. We imagine taking sequences of something like 20 visits in each of 3 different filters, and then basically moving between the fields so that we get sampling on timescales of minutes, hours, and nights. And we take many repeated observations so that we can check the internal astrometric and photometric calibration, build templates for difference imaging, and also start testing our coads. This gives an example of what one of those individual fields might look like. So given the ComCam field of view would be roughly 1 square degree. And just to give a sense, we expect to take something like 90 visits per hour. So you can actually get to some, comparable to LSST 1 year depth, and just a, even 1 hour will get you close to that point. This is just an example of what the fields look like. Through doing these observation simulations, we found that it's really valuable to have a whole menu of candidate fields that are distributed in right ascension. And typically, we'll observe something like, if you were to just run the scheduler the whole night, you might observe 8 different fields, for example, over the course of one night. This is what the images might look like. These are simulated images that were produced for the operations rehearsals for commissioning. So what we did during the operations rehearsals is that we took an observation simulation like the one that was shown just a moment ago, and we would simulate the pixel images and then play them back through the full data acquisition system starting from the summit. And then they would go to USDF here and go through the full set of pipeline processing. So this is just to give a sense of what fields with different stellar densities might look like. We would be intentionally trying to span a range of stellar densities like this, or perhaps even more. And this is an example of what just a small portion of what one of those dithered small fields with ComCam might look like, just to give a sense of the data. Okay, any questions about the on-sky observing programs during ComCam? I see a question from Michael, if there's a mic runner.
This is just a question of my ignorance. Are the physical filters to be used in ComCam the same physical filters that are used in the big camera, or are they smaller versions of that?
It's a different piece of glass, yeah, right? So appropriately sized for ComCam, but I'm confirming with Brian here. It's the same band pass to the best of our, in terms of the coding, correct? Same manufacturer. Yeah, so Brian Stalder is confirming that it was the same manufacturer, same formula for the coding of the ComCam filters and the LSSTCam filters, but different pieces of glass. Yep.
So Keith, I wanted to ask, having seen the sort of interleaving between the pinhole and the other filters and the limitations on zenith angle, is the pinhole camera expected to be on for a variety long enough to test many zenith angles in terms of looking for scattered light that doesn't come from the camera but comes from the building?
Yeah, that's a good question. So doing a filter swap is a daytime activity. So if we found that was useful, we could do it during the day. You can't do it during the night. And so I think it would. What we're doing right now actually is we're actively in the process of taking all these different types of observations that are planned during ComCam and actually weaving them into a schedule, starting with the first couple weeks, but then looking further out into ComCam. So I think this is exactly the type of question that we'd be thinking about as we're planning that out in detail. We're getting to the point of actually like the concrete night plans, what those look like. And we'll talk more about that, the process of how that happens later. Any other questions? Oh, a question on Slack. Can someone unmute or read it out? Okay, so the question was, will there be opportunities for input from in-kind contributors or the community on exactly which fields? So we have not defined an explicit process for doing this. In 2020, we collected commissioning notes from the community, and multiple science collaborations submitted those notes, and all of that input has been folded into the planning. We have, at this stage, I would say that the input would be pretty fine-grained in terms of thinking about like the exact details of the pointing centers. We haven't defined a way to collect input on this, partly because at this point we're really focused on what's needed for commissioning. So maybe I'll leave that as a TBD, because I don't want to overpromise. It's not to say that we wouldn't do this, but we haven't defined a process for this yet. Okay, I'm gonna hand over to Yusra to talk about science pipelines commissioning.
Thanks, Keith. So we're going to be using the science pipelines to commission the whole system. Yesterday, we talked about how the pipelines have tasks that are dedicated just to assessing data quality, and we're going to be running these pipelines that will produce plots and metrics to assess data quality throughout commissioning, to commission the whole system. But at the same time, we're going to be commissioning the pipelines themselves. We promise everything that we could do with precursor data, we have done with precursor data. And the pipelines are performing well with simulated data, DCAM, HSC, but every time you run the pipelines on a new telescope, camera, change up your survey strategy, you have to go through a short commissioning phase to tune config parameters, build models like the illumination correction model, the camera distortion model. And there's always some unknowns about your system, like what do the ghosts really look like? What do the PSFs really look like? What do the extended star halos look like? Which means that we have to do these checks every time we boot up for a new system. Now, you've heard this from multiple people. We're treating ComCam as a precursor data set itself. So a lot of these activities, we will not have to redo. We will have to redo them for most of them for LSSTCam, some of them to a greater extent than others. Our goal is not commissioning ComCam itself, but using ComCam to commission the whole system. And so when we get to the point with ComCam that we feel like we're getting diminishing returns and we're not learning anything about LSSTCam, we're going to focus our attention to something else. So we went through this procedure for a new camera a few months ago. We were getting ready for the operations rehearsals where we added simulated ComCam to our repertoire, and commissioning the pipelines for this went well. It took on order a month to get everything ready as a data point. Okay, so like I said, we're going to be commissioning the pipelines themselves and using the pipelines to do commissioning. And when you change the data quality and the science quality metrics will change as a result of changing your algorithms or changing hardware, changing camera, changing survey strategy, changing what field you're looking at on the sky. And we have to see how changing all these things affects the data quality together at the same time using the same observations. And this is quite a complex, this is quite a complex problem. And we are doing our best to consolidate and coordinate to best understand how all these factors affect data quality. So to this end, there are going to be a number of pipelines that get regularly run on the data as it's rolling off the telescope. And I went through these a little bit yesterday, but there's the quick look pipeline, which runs in real time to support observers at the summit. It has an image monitor, for example. There's the Reil alert production pipeline will also be running at the USDF. And this is for commissioning the pipelines and getting more metrics on data as it rolls in. We'll be also running a nightly validation pipeline. This is data release production flavored and serves to give us a report of what happened last night so that we can make decisions about what to observe tonight. And then finally, every couple weeks, we'll batch up data taken for the last few number of days, couple weeks. And we haven't worked out the exact appropriate cadence for this, but 2 weeks, and run a full data release production on that so that with the global calibration and see how everything is performing together. There's a Confluence page linked here, which has all the campaigns that we have planned and are running now. These are the campaigns that the campaign management team is responsible for. It will also tell you the collection names of the data coming out, who's responsible for piloting it, who's your point of contact. Each one of these campaigns has a little committee of representatives from pipelines, middleware, the verification and validation team to make decisions on what version of software to use, et cetera. So a lot of the same folks who are going to be doing the pipelines commissioning are also doing the commissioning with pipelines. And they're going to be very busy. And I think we're going to transition now to how you can get involved. And I'll hand off to Keith now.
Thanks, Yusra. Yeah. Okay, so we have a big task ahead of us because of the richness and the complexity and the volume of data and all the different data products that need to be produced to show that we're ready for to begin the LSST survey. And so because of this enormous breadth, in order to try to make this a bit more tractable, we have a bit of a hierarchical organization where we have established this set of 14 science units. And so you can think about these as, sort of individual working groups. They're very permeable. Each one of them has a lead who's typically a science pipeline developer who's the expert in that particular aspect of data processing or that particular data product. And collectively, we're hoping that these teams will facilitate bringing together expertise and experience from across the project, as well as in-kind contributors that have volunteered their time to help us with this really interesting, exciting, challenging phase of commissioning. And so each one of these science units, they have had over the past year sort of different approaches in terms of starting to prepare, and the activity is going to be ramping up quite a bit as we get to the ComCam on Sky commissioning phase. In terms of how to get involved, last year, May 2023, we held a commissioning science validation boot camp. This is a summary slide from that boot camp. And so this was 3 days where it was open to the whole community, but we were specifically trying to provide information to help in-kind contributors understand in a little bit more detail how they could plug into the effort and get involved. So the learning objectives were pretty specific. we had one goal is that they would understand how they could submit a pull request to the analysis tools package that would implement a science validation metric or plot. And while this was a very concrete objective, it was a way of helping individuals learn about how to contribute to the science pipelines, what that entire workflow looks like. We also had a learning goal that the participants would be able to contribute to a tech note, which is our way of providing open technical documentation that's visible on the web, because this is one of the main ways that we hope to be documenting our increasing knowledge of the system as we're going through the commissioning period. During the operations rehearsals that took place in April and in June, we also were folding in the in-kind contributors into part of this whole commissioning process and integration of all the different parts of the software, data transfer, data pipelines, visualization. And so we held co-working sessions during that period, and we suggested that individuals could work on two types of tickets, and this is the same type of tickets that on the project that we use. So we're all working together as one team. So one type of ticket is a task that is answering a question. This is not necessarily going to lead to a pull request on any particular science pipelines package, but what it could do is produce, for example, a notebook that would show the results of some study, and the goal would be to answer some question. And we expect that these types of analyses are going to produce verification artifacts, and I'll talk about that more in the next section. The other type of ticket would be to actually fix some kind of problem, to add a new feature, to make some kind of improvement in the science pipelines. So for example, this could be adding one of those new plots or metrics to analysis tools. So because that would be a contribution to production code that is run regularly through, as part of the science pipelines data reduction, this would go through the full data management workflow. There's a detailed developer guide that walks through how to do this. And we had these co-working sessions so that people could work side by side with one of the science pipelines developers and get more comfortable with how to go through this process. So in general, our guidance is that if you're one of the in-kind contributors, please consult with your science unit leads about the suggested tasks and what would be the relevant dashboard to see what are the issues that might be ready to be worked. Okay, so when we talk about the system, Rubin Observatory system, the system includes the hardware, the software, and the people that make the observatory run. And that includes all the operations at the summit. It includes all the operations at the data processing centers. And so one of the things that we've been focusing on in the past year is thinking really specifically about what is our concept of operations? What are the specific meetings? What are the communications? What are the information flows that allow us to work efficiently together when we're solving a really complex problem with a globally distributed team? And we're trying to do this on a very fast time scale. So the next set of slides show a list of meeting series that we have planned for the start of ComCam on-sky commissioning, and particularly focusing on the ones that would be perhaps most relevant, most interesting for in-kind contributors that are working on data analysis from remote locations. I put an emphasis here planned at the start because this may evolve depending on what we learn. This is informed by what we, the lessons learned from the operations rehearsals, but we may need to refine this. So in these slides, the meetings are listed in the approximate order, going from meetings that are intended for broad participation across the project team, and then narrowing down to very specific meetings that may have an expectation of deep engagement and work on very time-sensitive operational tasks. So we list those for context, but those really have a very specific goal that they're trying to accomplish. Due to the information sharing boundary conditions, these meetings will be open only to project team members. So that's the Rubin Observatory staff and the approved in-kind contributors once we're in the on-sky commissioning phase. And finally, I'd like to mention that to the extent possible, we're trying to subtract meetings we realize that people need uninterrupted focus time. And so we're trying to make more use of reports and trying to give space for people to think deeply about problems. So this actually requires quite a bit of care to do this. Okay, so starting off with the meetings with broad project team participation. The first of these is our CitCom General Assembly. We've been doing this for several years now. And the purpose of this meeting is to provide this overall vision on a monthly basis of the major activities and the priorities for CitCom during the upcoming months. This is participation of all members across the Rubin Observatory CitCom team, and kind of contributors are encouraged to attend this. And this typically happens on the first Wednesday of the month. Next are the meetings that are directly related to science verification and validation. So this could be a dedicated science unit meeting, for one of those individual groups, as suggested by a science unit lead. It could be another meeting that they suggest to go to. And so these are definitely places where the science unit members are encouraged to participate. In addition to that, we experimented during the operations rehearsals with hosting a sort of a cross science validation co-working time. And the plan is to do this weekly, probably Wednesday morning, at least Pacific time. And again, this would be work in topically focused breakout rooms, opportunities for people to interact and have a chance to work and learn from each other. Next set of meetings is going further down into the science pipelines development. So one of the meetings here is the science pipelines pair coding. And this has the goal of facilitating science pipelines development. So it's intended for people who are actively working on one of the science pipelines development tasks. You could think about this as it's ticketed work that's following the DM development guide, and also for people who can help others with those tasks. So if you want to, if you have a pull request and you want to merge to LSST distrib, which is the body of the production stack, this is the best way. This is the place to go to learn how to do that merge, working closely with one of the developers. This typically happens on Wednesdays. And then going further down, now we're getting into sort of more of the operational aspects. So it would be the science observation planning. If those of you have already been attending the data reduction and planning meeting, this is kind of a re-emphasis or rebranding of that. This is working through the strategy of exactly what tests need to be implemented as observing blocks for the on-sky commissioning. And so the intended audience here is the commissioning scientists who will be working to implement those observations, and then the product owners of the commissioning tests. We also have a data production stand-up. This is going even further down into the operations. This is intended to triage emergent issues, to assign high priority tickets, and supporting the 24-hour operation cycle. So this is all the decisions that need to be made on a short time scale to make sure that we are pushing data through the various pipelines. So this is for people who are actively working on a ticket, or where they can take a ticket and a response is expected on something like a 24 to 48-hour time scale. This is a daily stand-up meeting, so a very strict agenda, a very, very clear purpose for what this is trying to deliver. And then continuing on the summit operations, which is where things get most sensitive, we have the CitCom night test planning. So this is where the commissioning scientists are going through the detailed set of observations and are putting together the specific night plans that are coming up over the next week. They're actively working on the most urgent observing blocks, making sure that we are ready for on-sky observations. And then this is accompanied by a weekly test planning, which is trying to make sure that we're looking ahead, we're looking where we've been, making sure that we're making the right strategic decisions on a weekly timescale. Any questions about that? heard it. We can take the question from Anya's.
Great, thank you. So, yeah, because a lot of the kind of communication of findings and stuff like that will go through tickets and also like seeing what's urgent and what needs to be worked on. It might be useful to have like a place with a very simple introduction on how to create and also tag those tickets, because I think that will be very important. That, for instance, people who work on calibrations, they need to know that's like a calibration urgent issue or these kind of things. And I think it's not super easy sometimes to deal with the Jira.
Yeah. So I might let Yusra chime in on this as well. So during the operations rehearsals, we experimented with using during this data production stand-up to have a dashboard that we were working from, so that it was really clear what the tickets were, how we would triage them. And so I would expect that we would do something similar with ComCam, and that there may be instances where we see some issue in the data and we know that that's going to be a specific request on the camera calibration side, or that it might be something that's difficult to diagnose, and we realize that we have to have some triage process to define who's going to work it. So that process may iterate a bit, but that's at least what we have started from. Other questions? Oh, would you like to unmute yourself, online person? Sorry. or maybe Yusra can read it.
Maybe Yusra's meeting me. I wanted to, I sort of put in the Slack the JWST infographic that I think they did a really good job, because it was really communicating to the community, but the public liked it as well, what the status of commissioning was. I was asking about the pipelines, especially thinking about those and it's a graphic of basically steps that you need to complete for something to be done. And that there's no dates when you see it, but the thing like when you hit the milestone, say solar system processing can associate with a no moving object, well, that gets lit up, right? So I don't know the dates when things should happen, but I know that things are progressing because you see something lighting up when a milestone that's relevant towards getting towards something, a pipeline being completed, would be there. And so they did that for the instrumentation. It was really good about people understanding where things were without knowing whether something was delayed or not. I was just wondering if there's some thought about how to communicate to the community how you're progressing, right? With the way that we don't know the details, but we can see there's progress without having to bother people, right? And get a sense for like, oh, wow, we see it's coming, right? Or we can see that there's progress without, because it feels like there'll be a kind of a wall of silence where maybe there are small amounts of information that could be given about how a pipeline's progressing, or some check was completed. And I was just wondering if there's been some thought of that for the community, of how to do that in a way that also gives you the protection of not giving details because you don't want to promise things, because there's always things that come up in commissioning that'll delay. So just more a question about, has anyone thought about how you'll communicate with us, and whether what JWST did is a way that might be able to be used for these kind of pipeline sort of commissioning for LSSTCam and ComCam.
Yeah, that's right. I think this is Meg maybe asking the question. So we have started having discussions about that, and we've had discussions actually together with communications and education and public outreach, and we haven't decided on exactly how we're going to do this, but we have had the concept of a few different audiences, where one of the audiences is sort of the general public, and then there's another audience which is the science community. And we have talked about strategies that we could on a regular basis be providing information specifically to the science community at a slightly more technical level. We've at least we've been talking about the idea of including regular updates in the digests that are currently coming out every other week, or potentially having something on the community forum. We have, I'd say these are still discussions, so I don't want to commit to something specific, but it's definitely been on our mind, and suggestions on how to do that most effectively would be welcome and appreciated. Okay, I'm looking at the time, and I want to make sure that we have enough time to touch on some of the topics later in the agenda. So this next section is on the guidelines for preparing the science performance verification and validation tests and artifacts. So just some quick definitions to make sure that we're all on the same page. When we talk about verification, this is asking about whether the system meets the design specifications. Validation is, does the system do what the stakeholders want or expect it to do? Right, so this can evolve with the scientific landscape and the expectations of the community. And then characterization, which is understanding the system at a deep enough level that we can continually optimize the performance. So during commissioning, we will be engaging in all three of these areas. And the part that I want to focus on right now is on the verification, because this is part of the delivery of a completed construction project. And so I want to talk about our plans for how to do that and how in-kind contributors can get involved. So this is a preliminary diagram that shows the planned sequence of construction completeness reviews. So the big picture here is that over the next year plus, there's going to be a kind of staged approach where, as we are learning more about the observatory and its delivered performance, we will be going through and progressively verifying different aspects of the system, and basically, moving closer and closer into a full operational state. And so we have this sequence of reviews that will allow us to show that progress that we're making over the next year. And as part of that sequence of reviews, we are starting to think very specifically about what are the requirements, what are the specific aspects of the system functional and performance that we want to be showing as we are progressing through the commissioning phase. And so the workflow for doing that verification with a specific focus on the requirements related to the science performance. So we have a series of steps that I'll try to walk through here quickly. So the first step is basically taking these system level requirements and splitting them up into individual verification tickets that can be assigned for someone to work. And this is done. It's already been completed by the verification team. Then there's a step where we prepare the test case to be executed. This is sort of the systems engineering language for basically planning, what is the data that's needed? What is the analysis that needs to be done? What is the success criteria? And so what we would then do is take that input and develop a verification plan. This is what has been going into our system on Sky test plan. That then translates to the sitcom and block tickets that actually execute the tests to acquire the observations that we need. And then this gets folded into the night plan, basically following that workflow that we talked about previously. Along with that, there's the development of the science analysis software to measure the quantities that we need to about the data. And so, for example, we saw many examples earlier in this meeting of the analysis tools, which is a way of automatically computing these metrics and producing visualizations that's already being integrated into the science pipelines. So once we have the data and the software tools to analyze them, then we generate the verification artifacts. And this is expected to be one of the primary deliverables of the science units, is generating these artifacts that provide the evidence that we have met the specification. And then the systems engineering will collect those verification artifacts and produce the final reports. So the step one of that workflow was basically enumerating all of the verification tickets and assigning them to the science units to be worked. And so this is a snapshot of a dashboard that shows all of this. In total, there's 230 verification tickets that are related to the high-level science performance of the observatory, and that's why we have this large group of scientists that are going to be working on this. And then in step 5, this is the generation of those verification artifacts. So there's a tech note CitCom TN 102, which is a helpful document that provides guidelines and a template for preparing these verification artifacts. It mainly draws from examples that were used during the telescope and M1, M3 system performance analysis. For the science performance verification, I'll show some examples on the next slide. We're expecting that the artifact in this case is typically going to be a tech note, so one of these online documents, or it could be a Jupyter notebook, but something that can be exported into a PDF, so it's an actual, physical, document that we can attach at a moment of time. So the typical elements of the report, the artifact would be the related requirements, the execution details in the data, with the provenance that would allow someone to understand fully what data was used, the analysis, the results, and the conclusion. And importantly, the conclusion as a pass-fail statement about, did we meet the criterion for the specific test. This is an example of what one of those notebooks might look like, showing some screenshots. This was an example that was produced by Jeff Carlin, who's the verification scientist for the data management team. We thought that this would be perhaps more accessible to scientists because it's a little bit more closely related to accessing the Butler, accessing the data products, and performing an analysis. So some of the features to highlight here is that the notebook opens with a clear statement about what the verification ticket is, what are the specifications to be met. It also has the results, and it has a clearly labeled plot. It shows what the threshold is, it shows the performance, and it has a discussion about how to interpret the results with a final statement that says we consider this to be a pass. So we're basically looking for the science units to be able to prepare documents like this for each one of the tickets, and there's some other example notebooks that are linked here. In terms of the verification strategy, we're trying to take a pragmatic approach. That we are have a job to do, and it's a challenging job, and we're trying to do it as efficiently and as carefully as possible. And so during commissioning, our objective of the verification is to show that the as-built system is capable of accomplishing the LSST, that we are ready to enter operations. And so we are trying to encourage beginning these verification analyses as soon as we can, including developing as much of the analysis itself using ComCam data. We want to close out the verification tickets and then move on to further validation and characterization. It's not the last time we'll be looking at the data, but we need to show that we're making regular progress over the next year. Also, the data set that we're using for the verification, it can be modestly sized, provided that it is representative or at least probes the extremes of conditions that we would encounter during operations. So there's a phrase you can keep it in mind: as much as needed, as few as possible. Right, is a guidance to make sure that we're making progress. Okay, any questions on that? Okay. So in just the last couple minutes, I want to talk about the information sharing during commissioning and just hit some of the high points. So this is a one-slide summary. The important thing to know here is that there are two documents that are key references for the information sharing policies. So the first is focused specifically on the policies and guidelines. It's titled Information Sharing During Commissioning, CitCom TN 076. Please read this carefully, all members of the project team who are going to be accessing data from commissioning. And then there's a second document that goes through some of the practical considerations and implementation, and that's called the Data Security for Rubin Communication Channels, DMTN 286. So the most concise summary of this is that pixel images should not be shared outside the project team during the commissioning embargo period. That embargo period extends at least 30 days for any observations that are taken of the sky, and prior to the system first light media event, all of the images are embargoed. There's just no pixel images should leave the project team until at least the media event, and then a 30-day window for data taken after that. Because we have this globally distributed team, we need ways of communicating. We need processes of making decisions quickly in our work. We have set up a project team Slack workspace that will be in place by the start of ComCam on-sky commissioning. The membership will consist of project staff and approved in-kind contributors, and several channels will move from the public LSSTC Slack workspace to this project team Slack workspace. That's the most significant change in our shared communication channels. For the remaining channels that are shared with the science community, almost all of these will remain open. And so, for example, Confluence, Jira, LSST.io that includes the technical documentation, including the tech notes, GitHub, these will remain in their present state. We will not be able to post pixel images in those spaces, but they will remain a resource both for the project and the community. So what we are asking is that both the community and the project team will have access to a lot of information besides the pixel data. We intend to be regularly producing the tech notes. We intend to provide some regular updates, as Meg was asking about earlier. There will be a lot of technical information that's available, and we are asking the community to understand that this is work in progress by colleagues and collaborators. And then the statement at the end, the status of commissioning will be shared frequently with the world. We are working out the exact strategy for how to do this, but our intent is to provide regular updates to the science community and to the general public as we're going through commissioning. And we are at time. Maybe just one or two questions.
So can people on Jira post like pictures of images when like they are trying to find something during this embargo period? Because anyone could see that, right?
Right, exactly. So one of the implications here is that we will not be able to post on-sky pixel images on Jira. So your Jira tickets will need to provide links to other secure spaces that would have the pixel images.
That people don't do that. I don't know. Yeah.
It is a challenge, and this is what we have to work with.
Just as a point of clarification, I think that answers the question. But for example, that means that when you write a tech note, like a postage stamp is not something you can put in.
There are a select few examples of pixel images that can appear, and it's only for some specific technical instances. So for example, like the out of focus donuts for AOS commissioning, where there's no information about the sky in them. And we have a review process that we'll have for the tech notes. But if there was any situation where there is a pixel image, you would have to link to another secure place for that image rather than having it appear in the tech note directly.
Thanks.
Will there be any siloing of data within the SITCom and commissioning teams? Like, for example, if you're working on commissioning, are you allowed to look at basically all of the commissioning data, or are you only supposed to look at the stuff that directly pertains, like tickets you're assigned, for example?
our intent is to make it fully open within the project team. But that project team is specifically people who have been approved to have access to proprietary data products during the embargo period. And I should clarify that the science units are permeable. They are intentionally designed to have expertise from across the project, and we anticipate that people may be contributing in multiple areas throughout the commissioning period. All right, well, I think we should close it up in the interest of time. I think a number of people have trips to the airport. Thanks again for coming to the session. Thanks for the great meeting, and we'll see you soon.